Okay, the warm-up for this section is actually a quiz about the topics and the ideas that we covered yesterday about the basics of probability. So here's the I can statement. I can compute the probability of something called a simple event. So we'll get into that in a few minutes, but let's do this warm-up. So let's run through this little quiz. I told you I ought to be able to answer a bunch of questions on the stuff we did yesterday. So probabilities are ratios. They are fundamentally ratios. They're fractions, so they can be expressed as fractions. And I put an asterisk by this one because that's the way we typically do it. Decimals or percents. We'll use all three kind of interchangeably, but again, we'll focus mostly on fractions because they do come from ratios. Events that have the same chance of occurring are called equally likely. Equally likely events. The set of all possible outcomes is called the sample space. It's just a fancy word for a list of all the possible outcomes. Jenna rolled a die 10 times and got 7 twos. She rolled a die 10 times and got 7 twos. She concluded that the probability of rolling a 2 is 7 out of 10, and it says which type of probability did Jenna compute? Was it a theoretical or was it an experimental? Remember, theoretical is what we expect to have happen. We expect to get a 7 or a 2 when we roll a die, only about a sixth of the time, not very often. She got a whole bunch of 2s, and she computed an experiment and then did the tally, the 7 over the trial's 10. So that was an experimental probability. And then number 5 says, is the following a proper probability model? Yes or no? And then explain your answer. There are actually quite a few reasons here why it may or may not be. So let's take a look here. Are all the outcomes listed? We'll assume so since we don't know what the experiment's about, but there are results of blue, red, and green. And then one probability is 1/4, another one is negative 1/4. Well, that's a problem right there. So the answer to this is no, it's not, because we've just broken one of the rules for probability. So one of the reasons would be we have a negative probability. We could leave it like that. This probability right here is 7/4, so that's another problem. 7/4 is bigger than 1, so we'd say probability bigger than 1. That's an issue. Okay. And then the other thing is, on a probability model, they have to add up to 1. And if you add those up here, these cancel each other out, and we end up 7/4. That's not 1. So we'd say do not add to 1. Okay. So we've got several issues with that one right there. Hopefully you can spot all of them. You'd only need one reason to say it's not a proper probability model. Okay, 6, we've got two questions. If an event is impossible, then its probability is, if it's never going to happen, its probability is 0. If it's an absolute sure thing, its probability is 1. Remember, things that don't happen very often are closer to 0. They have low probabilities, and things that happen pretty commonly, pretty frequently, their probabilities are pretty high. They're usually closer to 1. The tally of how many times an event has occurred is called its blank. And then a hint here, it starts with FRE, and the word there is frequency. Frequency. Okay, so another word for counting up how many times something happens, instead of saying tally, the technical word for it is the frequency. How often did it occur? Number 8, when we make a ratio of the number of times an event has occurred to the total number of trials, we call this the relative blank. Well, that would be the way we compute an experimental probability, but remember from yesterday, we call that the relative frequency. Another name for that is the relative frequency. Okay? Next one, number 9. The theoretical probability does not require an experiment, but it is simply based on all the possible outcomes. We take the number of ways an event can occur and we blank it by the number of total possible outcomes. Well, remember, we're making ratios here, so we use division problems, so we're going to divide by the number of total possible outcomes. Number 10, what button do you push on the TI 30XIIS to access the probability menu? PRB. That's the button we push. And let's see, what is the syntax to make the calculator generate random integers from 1 to 20? So we'd want to simulate, like a 20-sided die or something like that, or drawing 20 different number tiles from a bag or something. So that's going to be rand I, so that's for random integer, and then we want the lowest one to be 1 and the biggest one to be 20. So that would work just fine there. And then I want you to think about this. Think about the coin and dice experiments. The theoretical probabilities were what we blank to happen, and the experimental probabilities are what we blank, or are what blank happens when we conduct a probability experiment. So hopefully you caught that verbiage in the way I said that several times. So theoretical probabilities are what we expect to happen. We expect that to happen. It doesn't always happen, but that's what we expect based on, things being equally likely and different things like that, and how many outcomes there are. And then experimental probabilities are what actually happens when we conduct a probability experiment. So theoretical probabilities are what we expect to happen, and experimental probabilities are what actually happens, those relative frequencies that actually occur when we do the tallies over the trials. Okay, now let's talk about today's section. This is on simple events. So let's talk about what a simple event is. Sounds pretty simple, and it actually is. A simple event is a single outcome from a probability experiment that is conducted one trial at a time. So that's another thing that makes this very easy, is we're only going to do this one at a time. Simple events are usually the results of probability experiments that are, we're going to say this, they're really easy to describe and understand. And you'll see as we go through, we're going to use lots of examples like this. So rolling a die and recording the outcomes, flipping a coin, spinning a spinner, drawing a marble from a bag, maybe a bunch of different colors in there, and we pick one out and see what color it is. Picking an individual from a list, so choosing somebody out of a class or something like that, just at random. Okay, so simple events are usually calculated using theoretical probabilities. So let's write the word theoretical, theoretical. Okay, so again, we've got to have a pretty good reason to use an experimental probability. So we're going to use theoretical probabilities for the time being. This means we need to know how many outcomes are possible. We need to know how many outcomes are possible, because that's going to be the denominator of our ratio, and how many outcomes are in our desired event. So they're going to have to give us a description of what they want to have happen. Like, do we want to roll a 3? Do we want to roll ahead? Different things like that. So here's the first example of a simple probability. So a set of 20 cards is numbered 1 through 20. Suppose you pick a card at random without looking. So you've got this deck of 20 cards. You're just going to pull one out without looking. Find the probability of each event and write the fraction in simplest form. So we want to write it as a fraction, and we want to write it in simplest form. So probability of getting a 2. Well, remember, this is going to be theoretical probability. So there are 20 different outcomes, and we just want to know how many of them are 2s. Well, there's only one 2 in the deck, so that's the answer right there, and 1/20th doesn't simplify at all. Let's do the next one. What's the probability of getting a 2 or a 12? Well, again, there are 20 different cards we can choose from. We're going to pick one, but we only want a 2 or we want a 12. Well, there are two ways that can happen. We can pull out a 2 or we can pull out a 12. So there are two ways that can happen. So we'd reduce that to 1/10. So the probability would be 1/10. What's the probability of getting an even? Now remember, there are 20 different ones to choose from. Of the 20 cards, how many of them are even? So we want a 2, a 4, a 6, an 8, a 10, a 12, a 14, a 16, an 18, or a 20 would count. And if we counted those up, 10 of them are even, 10 of them are odd, so we'd get 10/20ths, which we would reduce to 1/2. So the probability of getting an even is 1 out of 2, and we'd expect that because half of them are even and half of them are odd. Now this one's kind of interesting. This one says, what's the probability of not getting a 2 or a 12? So anything is okay as long as it's not a 2 or a 12. So again, there are 20 different possibilities. Well, let's see, if we throw out a 2, we don't want that, and we don't want a 12, that would leave all the other numbers, so there are 18 other numbers. So it's kind of the opposite of this one right here. We want a 2 or a 12, there are only 2 of those, but there are 18 of these others, and then we'd want to reduce that, so that's going to be 9 out of 10. So while there's only a 1/10th chance of getting a 2 or a 12, there's a 9/10th chance, or a 90% chance of getting something that's not a 2 or a 12. Now this next one might be a little bit tough. We've got to remember back what factors are, so stop and think about what factors are. Factors of 20, those are numbers that go into 20 evenly. So that would be like, and I'm going to list them like this: 1 and 20, let's see, 2 and 10, Going to work my way to the inside. 3 doesn't go in there, 4 does. 4 goes in there 5 times, and that's it. So there are 6 of them. So out of the 20 cards, only 6 of them would be factors of 20. So that's going to end up being 3/10 once we reduce that. So those are simple events like we were talking about. Pretty easy to describe, pretty easy to understand. All we need to know is how many outcomes are possible. In this case, there were 20. And how many outcomes are in our desired event. So how many 2s were there? How many 2s or 12s were there? How many evens were there? Things like that. Now we're going to do another one. We're going to spin a spinner. So I've got a spinner over here, and we just need to look through here and figure out if we're going to use that spinner, we want to find the probability of each event, write it as a fraction in simplest form. So let's look through here. These are all different letters. And notice that the spinner is equally spaced. Now we're going to assume that this isn't warped or anything weird like that. If we spin it, it's equally likely to show up on any one of those. So there are 8 outcomes possible, and we would just want to know the probability of getting an S. Well, there's only one S, so that would be 1 outcome out of 8, and that right there is reduced. We don't have to do anything else. What's the probability of getting a vowel? Well, again, we're going to do the 8 outcomes all together, and let's check for vowels. We've got an O, and that's the only thing. There's only one vowel, so that's a reduced ratio right there, our reduced fraction, so we'd say 1/8. 1 out of 8 times we'd expect it to land on that. Again, theoretical probability there. Consonants. Consonants. Well, let's see. If there's one vowel, the rest of these are consonants, so that's going to be 7/8. 7 out of the 8 are consonants, so there's our probability. And then the last one is, what's the probability of spinning a letter that's made with a curve? Well, again, there's 8 outcomes that are possible. Let's take a look at the ones that are made with curves. So curve here, curve here, curve here, curve here. So that means these 5 are made with curves. Those 3 are made with straight lines. So that's going to be 5 out of 8. Okay, nothing to reduce there either. Okay, let's flip it over and take a look at the other side. Here's what it says. A marble is to be drawn from a bag containing 8 blue, 5 purple, 11 orange, and 6 red marbles. Construct a probability model for this situation. Write all fractions as non-reduced and reduced fractions. So we want to do both. We want to leave it in kind of that raw, unsimplified form, and then we want to reduce it. And you'll see why in just a minute. Okay, so let's make a probability model for this. So we've got blue, we've got purple, purple, orange, and we could use the first letters of this as long as there weren't any repeats. And then we've got red. Now, in order to figure out the probabilities, the frequencies are really easy. So I'm just going to say there are 8 of these, 5 of these, 11 of these, and 6 of these. Now here's where the probability model comes in. These are the outcomes. This is just kind of listing what their frequency is, like how often they occur. And then the relative frequency, or the probability, is going to be, we need to know on each one of these how many marbles were there altogether. So if we add these up, let's see, this is 17, another 5 would be 22, and another 8 would be 30. So there are 30 total. So 30 total. So we're going to put a 30 right here underneath each one of these. And again, it said we don't have to reduce it until the end. So let's do this. This would be 8 out of 30. This would be 5 out of 30. This is 11 out of 30. And this is 6 out of 30. Okay? Now, we're going to leave those right there, but we're also going to reduce it if that's possible. So 2 goes into both of those. That would be 4/15. 5 goes into both of those. 5 goes in here once, and 5 goes in there 6 times. That's just 11/30. There's nothing we can do about that one. And then 6/30, let's see here. 6 goes into both of those. 6 goes in there 1 time, and 5 times there. So there are the reduced probabilities. Now, check these. They're all between 0 and 1. And if you add those up, let's see, we'd have 8/30 plus 5/30. That's 13/30. 11/30, that would be 13/30 plus 11/30, 24/30, and then 6/30, 24 plus 6 is 30, so this would be 30/30. 30/30ths is 1. So this is a proper probability model. And you'll notice that it's a lot easier to add those fractions together with the common denominator right here in the non-reduced form than it would be to try and add those together. So that's one reason why we did that. So let's take a look here. Find the probability of each of these events, right, as a fraction in simplest form. So the probability of blue, well, that's this one right here. We already got that one. It's 4/15. Probability of red, that's this one right here. It's 1/5. It's the 6 out of 30. Probability of blue or red. So either one is okay. So what we'd want to do is we'd want to add those together, and you'll notice that it's way easier to add these two together right here. So let me highlight those two together than it would be to add like the 4/15 and the 1/5. So let's add those together. We end up with, let's see, altogether 8 plus 6 over 30. That's 14/30, and we're going to reduce that. 2 goes in here 7 times, and 2 goes in there 15 times. So we've got that one right there. Now, the last one says not orange and not red. So it can't be orange and it can't be red. So if it can't be orange and it can't be red, that means it's got to be purple or blue. That means we're going to add those together. So we're going to take the 8 and the 5 out of 30. So that's going to be 13/30ths, and 13/30ths doesn't reduce at all. Okay. That's enough that you can get started on the assignment. We'll come back and we'll do part 2 tomorrow as we kind of finish more of these simple events and kind of expanding our knowledge of some basic probability. So good luck with the assignment.